In this chapter, we're going to start looking at the theories of bonding and structure, and we're going to start looking at some of the geometry, so how these electrons organize themselves around the atom. And some of this comes into play with what we were talking about with orbitals, but we're going to make some adjustments. Chemistry and science in general is all about making predictions, testing those predictions, and then making adjustments to that. And that's exactly what we're going to see also in this chapter here. We're going to bring another theory, and it's called the valence shell electron pair repulsion, or VSEPR theory, where we're looking at, remember, electrons are negatively charged elements, subatomic particles. They're going to be two in each of the orbitals that we're talking about. And we have these different domains called bonding domains and non-bonding domains. All of these different domains that contain electrons, ideally, those electrons are going to be spread out as far away from each other as possible. So some of what was done during Schrodinger's equations and the creation of those orbitals were that there were geometric shapes that were defined through these equations. And that really aligns well with what we're going to be looking at with this VSEPR theory, in that we're trying to now take these ideas of these domains, or the valence shell electrons, and we're trying to push them as far apart away from each other in a three-dimensional shape as possible. So you'll see what I mean once we get started here. When we're talking about domains, we're talking about single, double, triple bonds. Those are all considered the same domain. So a single bond or a double bond or a triple bond, those are one electron domain unit. And then lone pair of electrons are another set of domains. But here, let's get more into this here in the next set of slides. We're looking at the VSEPR theory again, and those negative electrons are going to repel each other. And so the electron pairs are arranged to be furthest away from each other, and that's the lowest possible potential energy. And the systems tend to like to be at a lowest energy. What I'd like you to do, if you're at home or you have something available, ideally, you have some type of toothpick available, or something that you can kind of stick into something soft. I like to use toothpicks and marshmallows. What I'd like you to do is try to take a marshmallow as kind of your central atom, and then arrange toothpicks around them. So you'd have 2, 3, 4, 5, and 6 toothpicks that point out from that. You could use fruit snacks, you could use marshmallows, you could really use anything that's soft that a toothpick could stick into, and take a picture of your kind of creation. And remember that the idea is to get those electron pairs, those domains, which will be your toothpick, as far apart as possible. And I'd like you to use a description to describe what the shape and what the geometry you think that might be of your creation there, with 2, 3, 4, 5, and 6. Take a picture of some of those, post in our Blackboard space, and then we'll kind of talk about this, but we'll get into it. Please do this first before you continue on with the lecture slides, because it's not quite as fun then. The VSEPR theory assumes a few things: that the bonds are shared pairs of electrons. They're part of those orbitals we were talking about in previous lectures. The central atom will have 2, 3, 4, 5, or 6 pairs of electrons in the valence shell. Generally, we're not going to go above 6, at least not in this conversation. And the models include a central atom that will have an incomplete octet, which, like we were talking about in the last section, we have to add electrons from other atoms to fill those octets. They could have complete octets or extended octets, obviously, if we want to go beyond 4 different bonds to the 5 or 6 pairs of electrons. And those electron domains, again, are single lone pairs of electrons, single bonds, double bonds, or triple bonds. The double bonds and triple bonds just count as one electron domain, so they'll take up just one of those spots. The next set of slides kind of go through, again, those basic electron domains. So if you haven't completed that chart, please try this first before you go into this. It's just kind of a nice hands-on thing that will help you get a feel for what these shapes are and they look like. So I'm going to show you the 5 basic electron domains, and here we have the starting point for those 2 domains. This is the central atom, and you can see if it has 2 bonds on either side, this is going to be a linear shape. It's going to kind of look like this, and it's going to be linear. That's the kind of how you would describe that. If we have 3 domains, remember this is going to be a 360-degree angle. If we divide that by 2, we get 180-degree bond angles. Down here with 3 electron domains, the best way to separate these out is by 120-degree bond angles. That's 120 divided by 360, or sorry, excuse me, 360 divided by 3 would be 120. This is called trigonal planar. It's planar because these would be in the same plane as each other. So if this is, we're going to have the basically 120 degrees apart. Now this one always messes people up, and a lot of times people will make 90-degree bond angles, but in fact the best bond angle is 109.5 degrees. And this allows us to actually, they're not 90 degrees, they're actually bent down a little further. So these 3 kind of bend down, and this one comes straight up, and that's called a tetrahedral shape. This is a very common shape, and we're going to come back to this one quite a bit. And especially when we get to organic chemistry, this is the predominant shape you'll see most compounds make.
5 and 6, we're not going to spend much time on these. It's not something we see very often in biological compounds, but I did want to show you these shapes. You can see that both of these distribute the space around that central atom to have those different regions as far apart from each other as possible.
The other thing that we sometimes see, so these are where the electron domains might be. We also notice that lone pairs of electrons tend to take up more space than bonded electrons. So if we have chlorine and tin, we would actually take up these lone pair of electrons here are going to take up more space than the chlorine-tin bonds here in this space. So we wouldn't necessarily call this a trigonal planar shape because we don't count those non-bonded elements as part of our geometry for the molecule. It will have a role in the shape of the overall compound, but not necessarily, that's not how we count that for the domain. So we'll talk about that in a little bit, but this causes the bend in the molecule. And here's just some description of that again. If we have 2 nuclei, we have the blue here is showing us where we would expect to have electrons found. And because we have that positive charge on the other side, it's going to kind of bend those electrons and bring it towards and kind of focus it towards that other proton pack. But here on the bottom, non-bonding domains, they don't have that focal point. They are not able to kind of focus that electron down and kind of squish it down. So it ends up being more of a bell or a balloon shape on the side. It takes up more space as well, which pushes other non-bonding electron domains kind of away from it as well. In this slide, we kind of talk about where do those things end up going. And not all electron domain parts in the geometry are always created evenly. And especially when we have 1, 2, 3, 4, 5 bonding domains. Remember, we had different locations. We had equatorial positions and we have axial positions. The axial positions are 90 degrees apart from the equatorial, where the axial positions are 120 degrees. So lone pairs take up more space, so they'll go into the equatorial plane because if you remember, again, that was 120 degrees they had on that side. So they wouldn't go into the axial position. They'll go in the equatorial position where they'll have more space in that spot. Here's a description of what happens when we start to take away bonding domains versus the non-bonding domains or the lone pairs of electrons. So let's start with a number of bonding domains. We have the trigonal planar shape here. Boron trichloride is an example of this. We'd have the boron in the middle, the 3 chlorines on the outside. 120 degree bond angles. The shape is trigonal planar. Next we go down to 2 bonding domains, so the example before, and 1 non-bonding domain, this is actually going to be a nonlinear bent or V shape. So you could use either of those terms to describe that shape. And again, we're looking at the molecular structure is going to be bent because we're following where the atoms are in that structure. And so that's a bent structure. We're going to start with now looking at 4 bonding domains, so the starting point of the tetrahedron. If we take one of those bonded and make that a non-bonding domain, a lone pair of electrons, this becomes a trigonal pyramidal. So trigonal pyramid is the shape we have now. You notice it's kind of a pyramid where those 3 are pushed down below the axes of that central atom. So trigonal, and we have the bond angle is a little less than 109.5. So normally they're 109.5, but this pushes these other bonds a little bit more down, so it's just under 109.5. If we take 2 of those and we remove them, now you can see the backbone of the molecule is going to be a bent shape, and we're going to have these 2 non-bonded lone pairs of electrons. An example of this is water. This is why generally you'll see water drawn out as a bent shape, because you have these lone pairs of electrons on the top kind of pushing those hydrogen atoms down away from the oxygen. We're now going to transition from talking about shape to talking about the polarity between those 2 different covalent bonds and how that changes where the electron density is on a molecule. When we are talking about dipole moments, we discussed this in a previous lecture, where you have to have a side to the different positive or negative charged areas, and that gives us a dipole, or 2 poles of our group. We'll have a positive end and a negative end, and I'll show you some examples of this. One of the first things that we need to do is determine if there is going to be a bond, if there's going to be some polarity within that bond. The first step is I have taken the periodic table here and I've cut out a large part of it, so you'll notice that all of the transition metals are gone on the left side here. So we're just looking at the kind of right side. I've also pulled in hydrogen, and I've kind of put it in just this little square block. And what we'll notice here is that this is a mechanism that I use to know if there is a polar or nonpolar bond. We know that the noble gases are not going to be involved in bonding. They're completely happy by themselves without any added electrons or bondings, because we know that they're valence shell electrons, they're completely filled up. But what we kind of do is I like to think of helium as that star of the show, and it's going to be kind of the corner linchpin of this whole idea. And that is, we're not going to kind of use this in any bonds, but we're going to kind of look at it as that star, that prime kind of focus of the rest of the periodic table. We're going to think of this as these things are all in a show, kind of watching this star, and fluorine's in the front row. And fluorine has the highest electronegativity of any of the other elements on the periodic table. So it's the front row, and we have the second row is oxygen and chlorine, and these are the next highest, but they're relatively the same. They have a pretty close to each other electronegativity. And then we go to nitrogen, sulfur, and bromine. We have hydrogen, carbon, phosphorus, selenium, iodine. These are going to have relatively similar electronegativities if they're touching the same color line here. So this is one of those techniques that I'd like you to do and have a periodic table. It's a good habit to kind of just start crossing diagonal lines down that periodic table so that you can remember if, for example, fluorine and nitrogen are interacting in a bond, we know that fluorine is going to pull electrons towards it more. Or if we have silicon and oxygen, we know that silicon is going to lose electrons to the oxygen, so this will be more partially positive, this will be partially negative. So that's how you can use this chart to look at electronegativity. One of the other kind of tricky parts of this is that nonpolar molecules can have polar bonds. So here's an example: carbon and oxygen, and boron and chlorine, and carbon and chlorine. So let's look back here quick on this chart. We have carbon and oxygen. You can see there are a couple of jumps from different lines, so we know that's going to be polar, those are going to be polar bonds, carbon and chlorine, right? We have this kind of orangish line and the blue line. We had boron and I think it was chlorine. So we also are going to have very polar bonds here. So between these, right, the carbon was less polar than oxygen, so we can kind of draw this little arrow. Positive side is towards the carbon, and the negative side, the electrons are drawing towards where the arrow is pointing, towards the outside. So these are polar bonds between these molecules, but these aren't polar molecules because there's no dipole, there's no two poles. Both of the outsides are negative and the inside's positive, but there's not an end. So the part that is kind of missing is that one side or the other. The same with BCl3. There's a negative charge, kind of like a donut, and then a positive charge in the middle, but there's not an end. And this is the same here. There's a sphere of positive charge and a sphere of negative charge on the outside, but not in the middle. So we need something that has one side and the other side's the opposite charge, where it doesn't count if that other charge is kind of centralized in the middle. So these are symmetrical molecules, and because of that, those kind of dipoles cancel and there's not an end to it. So now I'd like to look at a few examples of where we do have polarity. Here we have oxygen, and remember there are lone pairs on the top of oxygen that are not being shown, and that's why we have this bent shape. But now we do, because of that, we have this positive end down here and a negative end towards the oxygen. So the dipole, you can see the arrow, we have a generally positive end down here, negative end on the top. This is not canceled then, and we do have an overall dipole. So we have a side of positive charge and a side of negative charge. Here's another example where nitrogen also has a lone pair on top, and we get this trigonal pyramid shape that also will provide a dipole for us. So water and ammonia, which are both of these molecules, both have non-bonding domains, and the dipoles don't cancel out, so the molecules are polar. All right, here's another question that is going through that bonding shape, and we're asking about what is the molecular domain geometry of this molecule that's described as M and X2, where both X atoms are bonded to M, and M also has 3 lone pairs of electrons. So what is the molecular domain geometry? We're going back to that right now. So then answer this, bring the answer to class, or post it in our Blackboard space. Here we actually have the same molecule, MX2, in which both X atoms are bonded to M, and M also has 2 lone pairs on it. What is the electron domain geometry of this molecule? Answer that and bring that to class or post on Blackboard. And that concludes what I wanted to talk to you about the valence shell electron repulsion model. And just to review that, this is an explanation of the shape of the molecules.
And the shape is very important for the function of the molecule and how the molecule behaves and reacts.